In this video, I'll go over the steps to testing a null hypothesis. So previously, we focused on descriptive statistics, which are ways to summarize and visualize data in meaningful ways. Here we're going to turn our focus to what's called inferential statistics. So inferential statistics involves using statistical analysis to test hypotheses, and it involves using sample data to make inferences and draw conclusions about a population. So some examples of inferential tests that we'll cover in the next several classes include chi-square analysis, correlation analysis, and t-tests. So in this video, I'm basically just covering the overall approach to hypothesis testing. So it's important to know that the type of inferential method that you'll choose should be driven by the types of variables that you're analyzing. So earlier in the course, we talked about independent variables and dependent variables, and we talked about the idea that they have different levels of measurement: nominal, ordinal, interval, and ratio. And we said that categorical data refers to primarily nominal and ordinal data. Continuous data is more like interval and ratio data. So basically, if you have two categorical variables that you're analyzing, both a categorical IV and a categorical DV, you would use what's known as a chi-square test, and that's what we'll cover in one of the next few videos. We'll also cover t-tests, which are what you would use if you have a categorical IV. So maybe you're looking at gender differences, or you're looking at a difference between your control group and your experimental group on some continuous DV. You would use a t-test to do that. You would use ANOVA if you have 3 or more categories, a t-test if you have 2 categories, but for this course we'll only cover t-tests. If you have both a continuous IV and a continuous DV, and you want to know what the relationship between those variables is, you could use correlation analysis. That's definitely something that we'll be covering. I'll touch on that a little bit in this video as well. A little bit more advanced than correlation is linear regression, but definitely a related method. And so, like I said, if you have a continuous IV and you want to use those values to try and predict group membership in some categorical DV, then you would use logistic regression. That's beyond the scope of this class, so we won't be covering that. I just wanted you to know that that's kind of the possibility that you would consider if you had a continuous IV categorical DV. I covered hypotheses in a previous video. In this video, I'm going to differentiate between what's known as substantive hypotheses and what I'll cover on the next slide, which are null and alternative hypotheses. So a substantive hypothesis is one that is observable, and it's a testable prediction of the result of a study. It's usually found in the introduction section of a research article. So some examples, the authors might say, we predict a positive association between self-efficacy and performance. Athletes who perform better will have higher self-efficacy. Another example, we predict there to be a gender difference in elementary school students' ability to memorize the names of countries. So that's what they would look like if they were written as substantive hypotheses. So basically the author's prediction of what they actually might see when they analyze their data. Null and alternative hypotheses are statistical hypotheses. These are worded in such a way that matches the statistical test. So just a little bit of notation. The null hypothesis we sometimes refer to with the symbol H0, H sub 0. And this predicts that there is no relationship, difference, or effect. So it would be worded as shown in purple and blue here. There is no correlation between self-efficacy and performance. There is no difference in the number of countries in South America that boys and girls are able to memorize. So again, a little bit more specific to the statistical test that's being done. So the alternative hypotheses would be, and by the way, we can use the symbol HA or H1 to refer to the alternative hypothesis. An alternative hypothesis predicts that there is a relationship, difference, or effect. So it's basically just worded in the opposite wording as the null hypothesis. So there is a correlation between self-efficacy and performance. There is a difference between the number, or in the number of countries in South America that boys and girls are able to memorize. We can also represent null and alternative hypotheses using symbols that are specific to, again, the statistical test that's being done. Null and alternative hypotheses should be written with the values of the population parameters. So for example, if we're looking at the difference between two population means, like the mean for boys, the mean for girls, we could use the numbers 1 and 2 to represent those two groups of people. And the null hypothesis would be mu1 equals mu2. The alternative would be mu1 does not equal mu2. So this symbol you see here that looks like kind of like a U, it's the Greek letter mu, which is like an M in Greek. For correlation, we use the Greek symbol rho, which I know it kind of looks like a lowercase p, but it's actually the Greek letter that would be pronounced as an R. So basically, rho equals 0 would be the null hypothesis. Rho does not equal 0 would be the alternative hypothesis. Remembering that, as we've said before, correlation coefficients can range from -1 to +1. And then I just have visual here kind of showing what different values of rho would look like if we graphed them as scatter plots. So when you have no correlation, there's just no apparent relationship between the x variable and the y variable. If you have -1, it's a perfect negative correlation as basically as y increases, x decreases, and the opposite of that would be +1, perfect positive correlation. So as x increases, also y increases. So here's also some other examples. So if we look at average January temperature versus longitude, so longitude is just sort of east-west around the world. Like there's really no relationship between temperature in January and just whether you're on one side of the world or the other. What does matter is latitude, which is how far above or below the equator, so how far north or south on the equator your location is. So as we know, countries that are farther north, like over here, are going to have lower January temperatures compared to countries that are closer to the equator, are going to have hotter temperatures in January. All right, so null hypothesis significance testing, and sometimes that's abbreviated NHST. So you may have heard some terms like p-values, statistical significance, especially as you've been reading different research articles for your reviews of literature. So the general approach of this is to test whether there's enough evidence to falsify or reject the null hypothesis. So it's a little bit like a criminal trial where we assume that the defendant is innocent until proven guilty. So it's kind of like that, where we're assuming that the null hypothesis is true unless we can find enough evidence to reject it. And by rejecting that null hypothesis, it means that there's evidence to support the alternative hypothesis. And remember that the alternative hypothesis is more in line with our substantive hypothesis, kind of what we're thinking is the interesting relationship or the interesting group difference that we're testing in our study. So here are the steps to the null hypothesis significance testing. The first step is to simply state the hypotheses, as we've shown before. The second step is to set what's called a critical value for the test statistic. So I'll show an example of this in a moment. So that's step 2. Step 3 is to calculate the test statistic, and this is based on your observed data. And what you're going to do is you're going to compare the test statistic with the critical value, and you're going to use that to make the decision whether you have enough evidence to reject the null hypothesis. Basically, if the test statistic has a bigger absolute value than the critical value, then you can reject the null hypothesis, meaning that you have enough evidence to support your alternative hypothesis, and therefore there's a statistically significant relationship or difference. Otherwise, so if the test statistic is smaller in absolute value than the critical value, then you would retain the null hypothesis and you would conclude that there's no significant relationship or difference. So let's see this as an example. I know that a lot of those ideas on the previous slide are a bit vague for now, so let's make this a little bit clearer. So our research question is, in cars, is there a correlation between horsepower and gas mileage? And here's some data. This is from the MT Cars data set on R with, I think, 32 or so cars. And it's just plotting each dot on the graph is representing a certain car model. And it's showing that car's gas mileage in miles per gallon and horsepower. All right, so here's the data from which that graph was created. So let's see, where's my car? I think my car is called a Maserati Bora. I think that's how you say that. Oh, no, there's my car. It's a Honda Civic. So pretty good gas mileage, pretty low in terms of horsepower. So we go and find that on the graph. Right there's my car, the lowest possible horsepower and pretty good gas mileage compared to the Maserati Bora, which is off the charts in horsepower, but not so good on gas mileage. All right, so the first step, as we said, was to state the hypotheses. So typically researchers do a non-directional test, which just means that we're not sure if the correlation is going to be positive or negative. We're not making that prediction ahead of time. We're just saying that there is going to be some correlation, whether it's negative or positive. So our alternative hypothesis is just written as not equal to, as opposed to saying it's less than 0 or greater than 0, which would be a directional test. Step 2, setting the critical value. So this depends on certain factors. If you take the statistics course here, you'll get more into the details on how to find the critical value, but just know for now that it depends on factors like sample size, and it depends on the specific statistical method being used. In this case, we're going to use correlation. And it also depends on the significance level. And this is a choice that the researcher makes. So typically in research articles that you've probably been reading, you'll see alpha is 0.05. That's probably the most common one, at least in the social sciences. In other disciplines, you might see 0.01 or 0.001 or even 0.10. So in our example, we're going to use alpha as 0.05, and we have n equals 32 cars. And what we can do is we can find this information from a table to find the critical value of the correlation coefficient R. And this isn't a very detailed table because it only has n ranging, like counting by fives. So we have 32 cars, so we're somewhere between 30 and 35. So our critical value is going to be somewhere between 0.335 and 0.361. You can actually look it up elsewhere. You can do this online. There's a lot of different websites that will do this for you. You can use Excel, you can use R. But anyway, the critical value for this specific example is going to be about 0.35. So basically any correlation bigger than 0.35 or smaller than negative 0.35, if it's negative, is going to be considered to be significant. So we put our critical values on this image here. So basically 0.35 on the positive side, negative 0.35 on the negative side. And so again, anything that falls beyond that is going to be considered to be in the rejection region, meaning that we're going to reject the null hypothesis and say that there is a significant correlation if it's bigger in absolute value than 0.35. All right, so the next step, step 3, is to go ahead and calculate the test statistic. So figuring out the test statistic depends on what statistical method's being used. Usually you'll use software like R or SPSS to find this for you, but you can calculate it by hand. And in our example, the R statistic, basically the correlation coefficient, is the covariance of x and y divided by the product of their standard deviations. And here are those values. I believe this is for, I believe x is gas mileage and y is horsepower. And when we do this calculation, we find the correlation coefficient to be negative 0.7, about negative 0.78, something like that. So we can basically just return to our image here. We find that the observed R, our obs, is more extreme. It's farther from 0 than our crit. So its absolute value is greater, 0.776 compared to 0.349. And so we can reject the null hypothesis. We can conclude that this is a significant relationship between gas mileage and horsepower. So our conclusion: there's a negative linear relationship between horsepower and gas mileage in cars. We can report our statistics and then say cars with greater horsepower tend to get poorer gas mileage. So you'll notice here I wrote P is less than 0.001. You might wonder, why didn't we say P is less than 0.05? Because that was our significance level that we decided on, alpha equals 0.05. That's true, but it is less than 0.05. It's also a lot less than that. It's even less than 0.001. So when reporting p-values, you should report them to be as close to what they truly are as possible. So what is a p-value? So one sort of just phrase to try and remember this is, if p is small, reject the null. So basically, if it's smaller than your significance level of 0.05, for example, then that means that you should have rejected the null hypothesis, and you're saying that you have enough evidence to support your alternative hypothesis. So what does the p-value actually mean? It's a little bit complicated. It's one of the most commonly made mistakes that people make in terms of interpreting the value of a statistic. But what a p-value is it's the probability of obtaining such an extreme value of the test statistic if the null hypothesis were true. So therefore, if p is small, you're saying that it's improbable based on your data. It's improbable and unlikely that the null hypothesis is true. So therefore, if p is small, reject the null. How to report results of null hypothesis testing. I'm just going to give a few examples for in text, in tables, in graphs, for different methods. We'll cover some more of these in a future video as well. But for correlation, you could just write the two variables, whatever they are, list them out. The two variables were positively correlated, and you report your R statistic, 0.49, your p-value, less than 0.01 in this case. The 55 is known as the degrees of freedom. It's not important to know that right now. It's basically just n minus 1. There was a significant effect of gender, with women receiving higher scores than men. So this would be for a t-test if you're doing a group comparison, like a gender comparison. So you report your t-statistic, degrees of freedom, what the t-statistic was, and then the p-value. And basically, all of reporting in APA format tends to take a similar format to what you see on the screen here, regardless of whether you're reporting a chi-square statistic or a t-statistic, an f statistics, or an R statistic. Lots of different types of statistics you could be reporting for inferential tests. In a table, if you're doing some like pre and post test comparisons for different variables, you might just report kind of the descriptive statistics, so means and standard deviations, sample sizes, and things like that. And then towards the right-hand side, what we see here is the t-statistic for the different t-tests being done here. And usually what your eye is drawn to the most is the p-value, because a lot of this can be kind of difficult to to conceptualize, but the p-value, you know, if it's less than 0.05, then you're concluding that there's a significant difference. And the only one that meets that criteria is the variable that I'm on now, right here, compensation pre versus post. There's a p-value of just a little bit less than 0.05. So we could say there's a significant difference between these two averages. So graphically, you might see in articles, the author will give bar plots to show the averages of the different experimental conditions, different groups of people. So we have I guess soccer players here. We have novice soccer players. We have outfield players. We have goalkeepers, and they're looking at differences in response accuracy on some cognitive test under different conditions of brain stimulation. And so what you should take from this is that they'll basically, a lot of times authors will show significant differences by using like a little asterisk to indicate, okay, there's a difference between these two conditions. There's a difference between the black and the white bar. Here there's differences among all of them. Here there's differences among all of them. Here you don't see any significant differences. So that's how you might interpret or just visualize group differences with bar plots. Correlation tables will typically list out all the variables that you're looking at correlations between, and then it will show what the correlation coefficients were. For example, between stress and stressors, it's 0.7. Between received support and variable 3, which is perceived support, it's positively related at 0.46. And there are little stars to indicate which ones are significant. And also this author chose to put some descriptive statistics, mean and standard deviation, for each of the 5 variables at the beginning. Similarly, we have another correlation table, just lots more correlations among 10 total variables, so you can take a look at that one as well. And then you could use for correlation a scatter plot to show just visually what the relationship is. You can show a line of best fit like you see in red, just to kind of clearly show that negative relationship between, as we said before, miles per gallon and horsepower. So it is possible to make errors of decision in null hypothesis testing. Keep in mind that the decision whether to reject the null hypothesis is based on probability, so there is always a chance that researchers could reject the null hypothesis when it's actually true, which is a type 1 error, or a researcher could not reject the null hypothesis when it's false and when they should reject it, and that would be a type 2 error. So just to summarize this idea, if in reality the null hypothesis is true, but you reject it, then that is a type 1 error known as a false positive. Basically, you're saying that there is a significant relationship or a significant difference, or like your drug significantly works, but it actually doesn't. And the opposite of that is if in reality the null hypothesis is false, but you retain it, that would be committing a type 2 error, false negative. Basically, it means that there really is some interesting finding, like maybe the drug really does work, and you're concluding that it doesn't. So it's a false negative. You're missing out on the opportunity to report some interesting finding. And then, obviously, the other options are you could make correct decisions. So you could retain the null hypothesis when it's true, which is a true negative, or you could reject the null hypothesis when it's false, which is also a correct decision known as a true positive. So just some other analogies to help make this point clear. If you're talking about a criminal law, like a criminal trial, and there's a jury that's going to decide whether the defendant is guilty or not guilty. So if in reality the defendant is innocent, but the jury finds them guilty, then that's committing a type 1 error. That's basically putting someone who's innocent maybe in prison for something that they didn't do. So that would be a type 1 error. If the defendant did the crime, but the jury finds them not guilty, basically you're setting someone free, or you're not sentencing someone who actually did do the crime, and that would be known as a type 2 error. And so then obviously you have the two correct decisions: guilty if they did the crime, not guilty if they are innocent. Medicine analogy. So if a doctor is trying to diagnose someone, or is checking someone and trying to decide whether they have some disease, if in reality the patient is healthy, but the doctor makes a positive diagnosis, and this is literally where this terminology comes from. So if they make a positive diagnosis, but the person's actually healthy, that's a false positive. So that could lead to them being treated for a disease that they don't have. If they do have the disease, but there's a negative diagnosis, so basically they're declared healthy even though they actually have the disease, that's known as a false negative, a type 2 error. So it may be that a type 1 error is worse than a type 2 error. It may be the opposite. It just really depends on the situation. In research, I guess it depends on kind of how important, how influential your findings could be to society, things like that. In the case of medicine, maybe, I guess depending on what the treatment is, it could be not so bad that someone's treated for a disease that they don't have. But if it's something like amputation or something like that, then that would be pretty bad to have to amputate a limb or something if they didn't actually have a problem. So it really just depends on the situation. You might think in medicine, like probably a type 2 error is worse because they're going to not be treated for a disease that they actually do have. Another example, home alarm system. So a false positive, a type 1 error would be if there's no problem but your alarm starts going off. A type 2 error would be if there actually is a robbery in progress and the alarm stays quiet. So in this example, I would say probably a type 2 error is worse because you're getting robbed and there's no response from the police because the alarm's not going off. And again, of course, you have your correct decisions. If there's an actual robbery, you want the alarm to sound. If there's no robbery, if everything's fine, you want the alarm to stay quiet. And that's it for hypothesis testing. I know that was a long video. Thank you very much for your attention.